Today's my birthday, so nobody can be mean to me if I mess anything up. So this presentation is on Hadoop. Who knows what Hadoop is? Wow. That's more than I thought. You're not allowed to talk. So I wanted to start off with a couple of things and see if you can guess what they have in common. So Twitter's who to follow, LinkedIn's people you may know, and Yahoo's Search Assist, which I don't know if anybody actually uses Yahoo's search, but if you do, what do those all have in common?
Hadoop.
Yeah, they all use Hadoop. They're processed on a daily basis generally, and so it means it's not real time, and you know, they just pre-process that stuff, and so whenever you go to these pages, they've already got it pre-calculated. So that's a common theme in Hadoop. You're pre-processing things. There's some notable Hadoop users on this page. So obviously Yahoo, LinkedIn, Facebook, Twitter. The New York Times does a lot of image processing and things like that. eHarmony. Anybody use them? I don't know.
I do.
Thought so. Baidu, which is China's largest search engine. And I almost forgot. Near Infinity on QL, yay. So Hadoop in the real world consists of a bunch of it covers a lot of different types of problems. And the first couple we saw were recommendation systems, right? And there's natural language processing and data warehousing, and I mentioned the New York Times image and video processing. Correlation engines, that's actually what QL and Clicks do over there, a lot of that kind of stuff. Is some of the stuff that we'll be using Hadoop and related projects for. Across a wide range of industries. Obviously, we're in the government sector mostly, but there's a lot of other things. The first three examples that I showed were obviously from the social networking with Twitter and LinkedIn and all that kind of stuff. There's a lot of research in academia about this kind of stuff, and big telecoms and finance, and do all kinds of stuff. And John Santoro would be very happy that all the finance is doing stock picking and market research and forecasting and things like that. A bit of history. Hadoop was inspired by Bigtable, Google Bigtable, and Google MapReduce, and those were two papers that Google published in 2004. And became sort of all the rage. Doug Cutting, who created Lucene, and he also happened to create Nutch, which is a distributed version, like a web crawler plus Lucene search engine. And he realized that he needed some way to distribute Lucene, because Lucene, as Aaron has amply demonstrated at QL, is not meant for billions and billions of documents. It's meant for hundreds of millions. And so that's why on QL, it's sharded. Aaron has done all this stuff, and Bill and all the guys have done all this stuff to shard Lucene across currently, 64 instances. And so Nutch tried to do that. And so now what we're doing is trying to use Hadoop to sort of get all of this kind of parallel processing for free. And the last thing is it's named after a stuffed elephant. All of these names, incidentally, are named after, like Lucene was named after Doug Cutting's wife's middle name, which I think is also her maiden name. Nutch was Doug's son's name for food. And his stuffed elephant was named Hadoop. So, apparently that's something that he likes to name open source projects after. So what exactly is Hadoop? An open source, batch and offline-oriented, data and I/O intensive, general-purpose framework for creating distributed applications that process huge amounts of data. Right. So if you look at that, obviously it's open source, it's Apache, offline batch. It's not something that you're going to put and plug into your Rails app and do queries against actively, because even if you have a massive cluster, about the fastest job you're going to get is on the order of 20 or 30 seconds, because it has to launch all these things across a distributed cluster and do that kind of stuff. Obviously not the kind of response time you are looking for, which is why the guys at Twitter and LinkedIn and all those guys pre-process this stuff and stuff it in something else. Maybe a relational database, maybe something like HBase, which is also built on top of a component of Hadoop. And it's distributed for distributed computing. It's not distributed in the sense of, using, we want to use Clojure because it will help us with all the threading and make all that stuff go away. No, it's distributing problems up and basically splitting them up and running them in parallel across a massive cluster, which could range from dozens of machines to hundreds or thousands of machines. So Yahoo's definition of huge is this. This is I think this is the latest data I could get. 25,000 machines over 10 clusters 3 petabytes of data. That's 3,000 terabytes. That's compressed and unreplicated data. That means that their compressed data is at least 9 petabytes, 9,000 terabytes. And that's before, or I'm sorry, for the replication factor in Hadoop is generally 3. So you can multiply that 3 petabytes by 3, you get 9 petabytes of compressed data. And I think I've heard that uncompressed is around 75 or 80 petabytes, which is kind of big.
What comes after a petabyte?
I don't know. Aaron?
Exabyte?
Exabyte? Yes, exabyte. So that's pretty huge. By comparison, Clicks currently has, what are we going to go up to? There's going to be 9 racks of 32 machines, ultimately.
We'll have about a petabyte online in HDFS.
Yeah. So it's nothing to sniff at, you know, over at QL. It's a pretty significant amount of thing. Obviously, Yahoo's on a different scale. What?
Scott, on the previous
Yes.
slide, you had 700 plus users.
Yes.
Jason was thinking that was the number of people who use Yahoo.
That's Yahoo search users.
So, what do you think that actually means?
I think that is people who are submitting Hadoop and Hive and Pig jobs and things like that.
So just like people who add Yahoo who
Doing analysis and back-end work and things like that. Yeah, I don't know exactly, but I just kind of took these statistics from somewhere else and, you know. So, yeah. So there's two major components of Hadoop, the distributed file system, HDFS, and the MapReduce system. We'll go over each one of these in turn. But first, what is Hadoop not? So I already touched on this a little bit. It's not a relational database. It's not a structured data store of any kind. It's not meant for online transaction processing like you'd expect on any kind of like a interaction-based website. So it's not even trying to compete or replace relational databases in that sense. It's not part of the, I think the guys who started this it's not part of the whole NoSQL deal where, oh, we're out to, you know, replace everything that's relational database because it's all bad. That's not the case. Hadoop was designed for massive scale processing of distributed applications. So because the comparisons are inevitable, what are some of the key characteristics? So on the left, you see Hadoop. And on the right, you see relational. So I took some of the what I thought were some of the really big characteristics. So with Hadoop, you scale out. You add more machines. That's how you scale it. It's almost a linear scaling. You add more machines, you have more capacity to both store data and to process it. Whereas in relational, typically you scale up by getting a bigger machine. Now, I did a presentation, I think it was last fall, on Hibernate shards, which is a way of trying to shard a relational database across multiple relational database instances and make it look like one thing, which, as I said in the bottom, is difficult at best, even in some of the stuff I was trying to do on a small scale. The way that you deal with data in Hadoop is key value pairs, basically maps. Think of it maps, versus tables, rows and columns in relational world. And another key characteristic is in Hadoop and MapReduce programming, you basically say how you want stuff done. You list the steps. You say, this is what I want done when you do the mapping. This is what I want done when you do the reducing. As opposed to relational, which is all supposed to be declarative. You say you have a query which is declarative in nature and says, here's what I want. You figure out the execution plan. With Hadoop, you're doing the execution plan. You're saying how to process this data. And as I mentioned before, offline for Hadoop and online real-time for relational databases. Okay, first, Hadoop distributed Chris.
Are you going to give an example of what it means to, I know what it means to map, but
yes.
What does it mean to reduce something?
Yeah, that's going to come up in a second, yeah.
Scott, real quick.
Yeah.
Some of the larger SQL databases do support online analytical processing. Like
Sure, OLAP stuff, yeah. But not on the scale that Hadoop does, I don't think. I could be wrong, but I don't think so.
Well, the only one that comes close is Greenplum, which is written on top of a MapReduce algorithm.
scale wise, sure, but they're not strictly limited to that. Well,
Well, the TISAs are the only thing that I know that come close.
Okay. Anyway, we don't need to get arguments. See, it's already we got the Hadoop people over here and the relational people over here, so it's going to be a fight afterwards. So you guys better prepare. I don't know. I'd be scared if I were Seth because Aaron's kind of mean. But anyway, HDFS. So the key characteristics: the data is distributed and replicated. I mentioned this earlier in the Yahoo example. Files are not stored contiguously on servers. They're broken up into what are called blocks or splits, okay, and they're replicated over multiple machines. So if you have, say, a file that's 1 terabyte, Hadoop, when you put it into Hadoop, will automatically break that up by default into blocks of 64 megs as the default block size, and it will distribute that across your cluster. And then it will take each one of those blocks and by default replicate it to at least 3 machines in that cluster, so that if machines go down, it doesn't matter, it's going to rebalance. It's going to say, oh, a machine's down, I need to take the blocks that were on that machine and move them over somewhere else. And so it's kind of self-healing like that, and when that machine were to come back on, or if you just added more nodes to scale out, then it automatically will rebalance your cluster for you. It's designed for large files. It's not, you don't want to start putting a lot of small files in there. It's optimized for streaming large files, meaning sequentially reading them and doing stuff with them. And it's not a native file system, but it does provide a command line utility to work with things using commands that are familiar to you in Unix or POSIX, or ls, cp, mv, stuff like that.
Okay, so if it's designed for large files and an individual record in what you guys are building over at QL is not a large record by itself, is the large file the entire index? Is that what they mean? Or
No.
how are your files large then?
So how you would think about it would be you would dump the entire contents of a table from wherever it's coming from in a single file output, and then you would move that terabyte file into Hadoop to do processing.
Okay.
That would be your source.
Okay.
Okay, so here's sort of a graphical example. If Aaron has, let's say that, and the file paths are sort of like Linux or Unix, where you have, /user/Aaron. Aaron has 2 files, data1 and data2.txt. Maybe Andrew has data3.txt. And these files have these corresponding blocks in them. And so if we have 4 nodes, this might be an example of how the distribution occurs for those blocks across the different nodes. And we can take a look and see real quick. So this is the Hadoop name node, sort of the graphical console into this, and you can browse this file system, and you can actually browse and see, okay, I've got user, blah, 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 I've got, all these different examples, and I've got a bunch of files in here, and I can go in here and I can see that, oh, this file is chunked up, I can view it in chunks. Okay, so chunks are, sort of like blocks and things like that, if you will. Okay, so I can look at things like that, or I can come over here and, it's way too big. Or I can come over here and say, not Haddock. Yeah, sure. Where am I? So I could say Hadoop, not Haddock. I don't know where that's coming from. I don't even know what that is. Hadoop fs-ls / So I could do something like that. If I wanted to create a directory, I could say make dir /data1. If I did that again, hey, it added data1 there. Okay, and I can do, fs-rmr data1. It is. So just to show that you can actually do that kind of stuff, okay? So as I mentioned before, when nodes fail, it's fault tolerant because of the replication and distribution. It rebalances files across the cluster, both when you add new nodes as well as when nodes die. For various reasons, maybe you get disk failures, and it's designed with that in mind. It's designed, if you have Yahoo with tens of thousands of machines, for example, it's expected that machines are going to fail. I think I read that, something like, I don't even know how many disks a day fail there. It's some ridiculous number. You probably know?
The statistic usually is you usually lose 1 disk a day per 1,000 spinning, or per 2,000 spinning disks.
So, yeah, I mean, that's a lot.
So if you have 8 disks in a machine and you have 10,000 machines.
Yep. So you're losing a lot of disks a day, and the nice thing about it is it just keeps working. I mean, on clicks, sometimes we've come in, and when the cluster was first getting set up, there were some problems with communications between the machines on the racks and things like that Aaron eventually figured out. But we'd come in and like 20 nodes are down, yet everything's still working. All the data's still there. You haven't lost anything, which is kind of cool. And as I mentioned before, you scale out, not scale up, just by adding new nodes. And that's where we have 4 racks right now, 32 machines. We're getting 9 more racks in addition to that. So that will just give us more data storage and more processing power. Okay, so I think that you asked, so this is going to get to what Chris just asked a couple of seconds ago. So in the MapReduce system, the paradigm is that you operate on file splits. You take the file and you split them. Now, HDFS has already done that for you, so the typical unit of splitting is a block. Okay, so that is a block. So you operate on one block of a file. And you operate on key value pairs. And the two key things to remember are that mappers filter and or transform data. And that reducers usually aggregate over the output of the mapper. So, and the other thing is that because you have all this data, it's like, let's say you have a file, you have terabytes and terabytes of data. If you want to do processing, what's the most efficient way to do processing across that cluster? It's not to move the data to where the code is to process it. It's to move the code to where the data is and do the processing there. And that's exactly how Hadoop works. It moves your code, your jar file, for example, and distributes it across the cluster and runs that code on all the different machines. And then you have centralized machines for monitoring that stuff. So this is sort of an illustration of how mapping and reducing works at a high level. In the map phase, you get a bunch of input pairs, K1 and V1. So they're your inputs, and you do something with them. You filter them, maybe you just drop them, maybe you transform them into key K2 and V2, a new set of keys and values. Okay, so once you've done that, then Hadoop takes care of shuffling that stuff over, or copying it over to the reducers. And what you get there is a grouping. So all of each reducer will see a grouping of key and all the values that were for that key K2. Okay, and I'll go through an example that will hopefully make this more clear in a second. And then the reducer is going to transform that into a different list of key value pairs. So the canonical example for Hadoop is always word counting, and so because it's a problem that suits itself well to distributing. So let's say that you had, I pulled down, I think what I showed earlier was a bunch of documents from the Project Gutenberg, just a bunch of free books, and I pulled them down to run the word count example against that. But let's say that we have this as our input. Okay, the quick brown fox jumped over the lazy brown dog. So let's go through each of those phases. The map inputs would be this. So by default, it's going to look something like this. Your keys might be meaningless. In this case, they are. They're the byte offsets into where those are. So this is 0 through 19. This is 20 through 31. This is 32 through whatever. And so in this case, we don't really care at all about those byte offsets. What we care about is the values. And what are we going to do with those values in order to count words? So this is where you declare how to do the processing. Okay, so you're going to tokenize it. Okay, you're going to tokenize that into tokens, and you're going to count, and you're going to basically do something like this. So for each token, I'm just basically going to say that is a list of K2, V2. The token is the word and the number 1. Why the number 1? So so this is the output of the mappers. So that's kind of confusing until you look at the, yeah.
So you map a block to, so you map one key value pair to a list of key value pairs. You might map one block to multiple key value pairs.
Yeah, right, exactly. So in this case, yeah, I mean, so what I'm showing here is sort of the aggregate map input and output. So here, this screen right here is the aggregate input, and that's the aggregate output of those 3 lines. And these could be, you could think of this being distributed across different blocks and things like that, and each one of those would be in a separate mapping machine, and you'd all, come together with these map phase outputs from all of them, and then you go to one or more reducers, and those reducers would see something that looks like this. So what it's going to do is going to take these. So for example, look at brown. We have brown 1 and brown 1. We have the 1 and the 1. We have 2 of those. So what ends up happening in the reduce phase is it sees something like this. So it groups the keys together. So you see brown, that key, now has a list of 1s, as well as, the has a list of 1s. Everything else just has 1s. So the way that you then reduce this is you aggregate over the values for each key. So if you have a given key, the, aggregate over these 2. In this case, it's going to be a sum operation, so you're going to reduce it down to something like that. So now the and brown are counted as 2 each. So that's how you get the word count.
On the previous slide, would you ever have an intermediate phase? Like I'm imagining, what if that list of values was like incredibly huge?
Yes, there is something called a combiner, which I will get to in a little bit. And it's like a reducer, but during the map phase.
there a general way? So you showed, a sentence was chunked up into those 3 pieces. How do you get these terabyte files into those 3 pieces? Is it through some previous run through a MapReducer that chunks it first?
No, it gives it to you because it basically, the mappers, you just declare, I need this input. You say what directory the input is, and it basically just gives you all the files that happen to be in that directory, and it basically takes care of the splitting up for you, like across the blocks and things like that. And I think Aaron wants to talk.
What if it split it right in the middle of the word the?
It depends on, there's some lower level stuff underneath here. That there's input formats and output formats. And so if you have a text input format and a text output format, and it's done by lines, the framework ensures that you get, contiguous lines and things like that. So the default would be line break, split and things like that. So it handles that stuff for you.
But can you change that if you want to?
You could write your own input format and your own output format, like the New York Times probably had to do if you're processing images and stuff like that, any kind of file format. You can do whatever you want.
Too. I mean, with the alignment on books, sometimes you'll get hyphenated words across lines.
Yep, exactly.
Okay.
So here's a little bit of code, although I'm just going to, this is for the backups. So let's actually skip over and go right to some code in here. Okay, so the template of a class to do your MapReduce job is going to look something like this. So you're going to have a top level class, and then you're going to have, actually let me collapse these so you can see the structure a little bit better. So then you're going to have generally a static class inside there that's going to be your mapper, and it's going to extend the mapper abstract class. And then you're going to have a reducer that extends the reducer, and then you're going to have what's called a driver, which actually sets up the job and runs it. So let's take a look at each one of these in turn. So this is going to do essentially what we just did in the word count stuff. So the map class is going to, basically there's one method that you implement, map. And all this kind of generic stuff is that's K1V1, remember? And that's K2V2, the types of those things. So the types of the input key and value and the type of the output key and value from the mapper. Okay, so in this case, we're going to take in, well, we don't care, that was a byte offset. Then we want text, which is a Hadoop class for basically a string. Then we're going to output the word as a string and the count as an int. And you're probably wondering why they're not just string and int and things like that. It's because in order for Hadoop to serialize all this stuff across the cluster, it has its own serialization mechanism, its own classes that implement the writable interface and things like that. And so the map class that does just what we said before, we're going to tokenize the value, which is going to be the whole, a line of input, and basically just walk through it, right? While the tokenizer has more tokens, set that word token and then write it out. So this context object provides the way that you do output. You say, by saying context.write, that means you're writing, in this case, the word out and the number 1. Remember how we said we're going to write the and 1 and the and 1 and the and 1 and brown and 1 and brown and 1. So that would be that process, okay? The reducer class looks something like this. So it has a method called reduce, and it also defines the types of input. So these two right here are the input key value types, and they need to kind of match what you're getting in from the mapper here. And here is the final job output. So we're saying that we're going to get in words and or strings and ints, and we're going to output strings and ints because we're going to say the final count will be words and the overall count. So in this case, the way that the way that this works is you create a sum, you iterate over the values that it gives you, and it's not like it's going to give it to you in a list. It gives it to you in an iterable because you don't actually know how it's coming. It's coming from all across the cluster. I'm not actually sure how it's implemented on the covers, although I'm sure Aaron is. But the idea is that you just keep getting the values through the iterable. And what's nice about iterable is that you can just use a simple for loop, the for each loop in Java. And so then we just write out the counts. And so that's how we get, so essentially for the case of the, we'd see the key the would come in, and the values iterable would give us 2 values, 1 and 1, and then we just sum them up. Okay. So the last thing is sort of this thing called the driver. In this case, I've just done it in a main method. And you go ahead and get a Hadoop configuration. You can do some processing of arguments. At the command line, you set up a job. You give it a name, a configuration and a name. you set some stuff like, okay, where is the jar that this map class or this class is coming from? What's the mapper class? What's the reducer class? What are the output keys and value classes? So you need to tell it how to store it in the files, because when it's done processing this, it's going to store it on HDFS in files, and it needs to know how to do that. In this case, we want to do store it as text and an int. And this is where, if we're using file input format and file output format, we're just saying, hey, give me the input path and the output path. So here the usage is just say input path and output path. And then launch the job. Say job, wait for completion. So if I go ahead and run this, so let me see, where am I? I want to be there. Okay, so the Hadoop command also allows you to run jobs from there. So we did Hadoop FS before. We're going to do Hadoop jar. That means run something in a jar file. Then tell me what is the jar file, in this case exploring hadoop.jar, and then what is the class name that we're going to run, so simple word count, and then the input and output. So this has to be, this is an input directory that contains files. So if you remember from earlier, when we went in here, we saw word count input is all of these files right here. Okay, so where I'm going to put this actually can't exist, so I'm going to call this demo1. Okay, so I'm going to go ahead and launch that. And what that's going to do is it's going to launch a MapReduce job. And so now we can come into the MapReduce administration console that Hadoop provides, and it tells you what the running jobs are. And then we can go and look at the job and monitor its progress. So we can see, okay, there were 10 map tasks, 8 are pending, 2 are running. Now, since this is all running on my local machine, only 2 can run concurrently. On, for example, our cluster at QL, I think it's what, 768 map, or what is it? 1,200 mappers could be running concurrently and 1,200 reducers. And also, because I'm running this in what's called pseudo-distributed mode, only on one machine, it's only going to allow one reducer. But as you can see, you basically get the completion graphs of the mappers and the reducers. And there's 3 different phases. In the reduce phase, once all the mappers gather their data, it copies them. So that's the copy phase. Then the sorting phase is when it takes those all the keys and sorts them together and puts them on the same reducer together. And the final thing is to do the actual reduce. Okay, so this was refreshing every 30 seconds. So it actually finished up. Okay, and we get some information about the job itself, how many bytes it processed, some counter things and stuff like that, how many map tasks complete and reduce tasks complete. So the output of that, is actually, if we go into demo 1, so because we had one reducer, there's going to be one output file. So the total number of output files of a job depends on the number of reducers. So I have one reducer, I have one output file. If I had 10 reducers, I'd have 10 output files. So in this case, you can see what it looks like is just like this. Now, this is a simple word count, so it's really not doing a lot of stuff to clean that up. I have a better one. And if I go back actually to the output directory, like so one of these, that's not right. 17. So this is an example of running a more advanced program where actually we're stripping out punctuation and stuff like that. So that's sort of a simple example of doing word counting on Hadoop. So this, as I said, we just went over this stuff.
You talked about, in this case, we had just one reducer.
Yeah.
Would it normally be Hadoop that decides if it wants to?
Okay, so you can either tell Hadoop the number of reducers, and there's certain algorithms that I can't remember exactly what they are. There's 2 different recommended values for the number of reducers. You can set it yourself, or if you're running a Hive job, which I'll get to later, it can estimate it from the size of the input data. So that's what you're trying to do. You're trying to estimate the number of reducers based on the size of the input data.
Scott, does your reducer need to be able to, like, because Hadoop could decide to run 1 or 2 copies of it, if you run 2 reducers, you would then need to further reduce those outputs eventually, right? I mean,
well, it depends. I mean, if you
because I guess they're going to sort the keys before they give it to reducers, so they would just need to join and potentially sort the output.
Well, if you have 2 reducers, you end up with 2 output files, and then you decide what you need to do with that. Do you need them to be combined, or can you just do something with that stuff like that? I mean, in the case of Hive, or a lot of times, you could, if you have 2 reducers, then if you chain that as input to another job, for example, Hadoop just says, oh, I just care about the input directory, and so now I have 2 files in there. Those 2 files would just, it'll automatically combine them and give them as input to, say, the next job or something like that. I didn't realize it was going to be taped, so this is a, I'll just put this up front. I stole these next two diagrams from Hadoop in Action. Please go buy the book. It's great.
Scott, just one quick stop question. In your reducer, I noticed that you had an instance variable for your int writable, and you just started resetting that one. Is that
yes.
Be expensive to create key?
Exactly. Exactly. And I did that there. Actually, let me open up this better word count, which is the one that does more stuff. But let me see. Actually, no. That was a bad idea because it's harder to see. But yeah, you're right. So for example, you're talking about that, right?
Yeah.
And we do the same type of thing up here in the mapper.
Right. I think there's a coding problem though, because you still create a new text token anyway. But yeah, same idea.
Oops. Yes, that should be word. Thank you. Yes. So the traditional wisdom is that garbage, or let the garbage collector do this. It doesn't matter. Object creation is irrelevant. And in web applications, it is. And as I have learned on clicks, that is not the case when you are processing billions and billions and tens of billions of records. It does make a difference. It makes a lot of difference. And so anything you can do to actually reduce the amount of objects created can make a difference when you're dealing with the data sets of these kind of sizes. So, yes, good question. All right, cool.
The way the writable frameworks work is as soon as write is called, you can reuse any of the objects that you've passed into them, and they're considered mutable so that you can change them over and over and over again. But Hadoop has snapshotted that and done something with it, so you're not going to destroy anything like down the line. It doesn't buffer.
Okay. Cool.
Yeah. So this is sort of a snapshot or a diagram of the general flow in the MapReduce. So just to reiterate, you have input data. That might be HDFS that's sitting up there. So it might already be there. It's distributed to the nodes. Well, not really, because it's already there. The code is distributed to the nodes. Each map task works on a split. So, for example, a block, okay, a block of stuff, and it outputs its intermediate data. Now, this process right here, I'll get to in a second. This is called the shuffling process, where it takes the keys and groups them together, and are all the values for a given key, and puts them over to the different reducers. And the reducers get that input, and then they store the output. What's in between there? So all this stuff right here is called partitioning. And that's the process of deciding which keys go to which reducer. And what you really want is an even distribution across the reducers, because if you have a case where you have data skew, and we actually had this case on QL, we were running a bunch of jobs, and all of a sudden, one reducer was getting completely overloaded. The other reducers would complete in like 5 or so minutes, something like that, whatever. And then one would just sit there and go for hours and hours and hours and never, ever complete. And the reason happened to be because we didn't realize that some of the files, because we have a ton of files, were actually in a were delimited differently. Instead of delimited, say, by commas, they were delimited by tabs. And so everything was getting lumped into the first column, which then we were looking at some other column. And so everything was getting to be null. So there was a whole lot of data where the keys were null. And it was skewed way, way, way such that there were so many that had null as the key that it was overloading that single reducer and basically just killing the job. The job couldn't complete. So you got to watch out for that. And here's an example I also stole from Hadoop in Action. Go buy the book. That I liked because I thought it was pretty good in that it's a good illustration. So you have all the inputs, and here are the mappers. And inside the mappers, you notice that all the different shapes. And the different shapes are the keys. So think of the shapes as keys. So I have a key of star, a key of oval, a key of square, and so forth. And inside the different shapes, the different keys are different values. And so in this process, what you see is, and don't think that there's always the same number of mappers and reducers. That's not true. It may be that you have 1,000 mappers and 500 reducers or something like that. So when all the mappers get done, basically the framework then says, okay, what keys go to which reducers? And it does that by default just by hashing the key, called a hashing partition scheme. And so you can see that all the ovals ended up on this reducer, all the hexagons ended up on this second reducer, and note also that the stars and the squares ended up on the third reducer, which shows you that because you don't necessarily have the same number of keys, you might have more than one set of keys or values for one key ending up on the same reducer. And so that's how
I thought the keys were less relevant. Because you said, like, in your example of
we ignored the input key.
We ignored the input key in that particular example because the input key for the word count example happened to be the byte offset. So when you're doing processing of text files like that, almost always you're going to ignore that byte offset.
But it would still sort them. Well, there would be no duplicate keys in that sense because there'd be unique offsets every time.
No, because the keys that get shuffled are basically the words in that case, not those. It's the output of the map. So the map keys are and brown and lazy and
those were the keys.
Yes,
So
exactly.
the reason why you would have keys and values as inputs to the system is because usually you chain multiple jobs together. So the outputs, which are keys and values from the reducers, feed the next job's inputs.
Okay, I was confusing that. The sorting here for the keys was the 0, the 10, the 20 for the offsets, and it's not. It's the actual tokens for the sentence. Okay.
So there's no coordination between the mappers and how they shuffle. It's all autonomous, and there's no central coordination.
Right. And it's designed like that because it's in parallel, and so.
Right.
It's all file based actually.
Yeah.
Files?
So each reducer actually copies one file from each output of each mapper.
So this is to answer Jeff's question earlier. It said, what if you have, in the word count example, you have, the appears 1,000,000 times on one mapper, and you're going to shuffle, you're going to copy the one 1,000,000 times. How do you deal with that? Well, you don't want that to happen. So in some problems, you can do what's called a combiner, and it's effectively a mini reduce or reduce on the map side before it actually goes to the reducer, which is why it's also called local reduce. So in the word count example, so without a combiner, it's shuffled. Let's say that you have a document or that sees a mapper that sees the word the 1,000 times. It would copy or shuffle to the reducers the pair the and one 1,000 times. But with a combiner, you could basically say, well, you know what? I could just add all those up, all the ones up, essentially do the same reduce process of summing them up, and end up with shuffling the and one time. And so that way you're reducing network traffic, which is going to make your job a lot faster. You've really alleviate the network traffic that's going around and so forth. And so I think this guy right here, this better word count, actually does that. I won't go through all of this, but I actually note right here the reducer class is a reduce, and I also have set the combiner class to reduce as well. Okay, and so the interesting thing about that is, let me go here and say run better word count demo 2. So we'll come back to that in a second, or actually we'll just go ahead and look at this job. So it hasn't even gotten to the point where it's going to do the counters. I'm waiting. Okay, see, we started getting a bunch of stuff here. And you can see these combine output records and combine input records. On the previous job, the combining stuff was all 0. But what's ending up happening is we're getting all these records in, and look how much of a reduction we're getting in what's being output to the reducers. So it's not done yet, but you can see that it's a significant reduction. In this case, 1.8 million records went into the combiners at the map phase from the map outputs, and that went down to 148,000. So that's a lot of reduction. So instead of shuffling over almost 2 million key value pairs over the network, I'm going to, in this case, shuffle 150,000.
Is there ever more than one combiner phase?
Not that I'm aware of.
Sense?
No, I think you have a map, and you can then apply a combiner to that job, and then it goes to the reducers.
The whole point of it is to reduce network traffic. So
So
and then you have to copy, so you don't want to copy more than once.
right.
Steve.
So your reducer had the same inputs and outputs. Is that always the case?
As the combiner? Or
well,
what do you mean the
same? What I'm getting at is reusing the reduce class as the combiner only worked because you had the same inputs as the outputs.
Right.
The reducer.
Yeah.
Is that always the case?
Well, it will have to be always the case, but
if you're going to reuse the class. class.
If you're going to reuse the class like that. Yeah, you could write a different type of combiner. In that case, it just happened to be nicely formatted for a demo so that you could use the same one. But
is it typical that you would have the same inputs and outputs for your reduce?
yeah. Because yeah, exactly. Because that's the whole purpose of the combiner is basically to do something. Because remember that reducers are for aggregating data. So a lot of aggregate operations are associative, or is it commutative? Which one am I thinking of? It basically says you can apply the same ones to different sets. So I can do it at the on the output of all those the 1, the 1, the 1. So I can sum that up and get the 1,000, and then I can take all of the 1,000, the 2,000, the 500 from all those other things and just sum them up. So sum basically doesn't matter whether I'm summing ones or whether I'm summing whatever numbers. It's still a sum.
Hey Scott, does a combiner always get called if you register it? Like, say a key only has one value for it anyway. Is it going to bother calling a combiner?
The key only has one value.
If locally on the map.
Well, what you do with the values is up to you, because remember I split the values to arrive at a different set of key values for the map.
Sure. Well, it's just the name combiner means, to me at least, if I have many values, I can combine them into something different. But if there's only one value, would it bother calling it?
I think it has to, right?
Yeah,
Because it doesn't
yes.
know that you're doing...
It doesn't, yeah, exactly. Dave's right.
know that
It doesn't know how many there are,
Right.
so
It's a single thing.
it's still going to apply the same thing.
Okay.
All right. Here's some advanced MapReduce, which I'm not going to cover at all because we don't have enough time, and I'm actually running short on time as it is. So Hadoop streaming lets you basically stream in other languages. Like you could write a mapper in Python or Ruby or whatever you wanted to, and it would talk between standard in and standard out. As we mentioned before, a lot of times you chain MapReduce jobs together. Joining data. Joining data is something you can do in code. Also, as we'll see later, you can do it with Hive, which is a way of doing essentially like SQL on top of MapReduce. Bloom filters are useful in joining data, and Aaron is actually using them on some stuff to reduce a lot of input data on clicks. Architecture, talked about HDFS and MapReduce, what's under them. So a bunch of different daemons, and all these different daemons run on all different machines. So here's sort of the high-level architecture. You have generally per cluster one name node. That holds all the metadata for the file system. What files there are and what blocks there are and where those blocks are. The job tracker tracks all the jobs. And the name node delegates to the data nodes. So the data nodes are on other machines in the cluster. They're actually the things that store the real data. And the job tracker delegates to task trackers. So what you typically have is you have a cluster that has one name node server, nothing else on it. You have a job tracker server, nothing else on it. And then you have some number of data node plus task tracker servers. And that's what they're doing. And so what ends up happening is, remember how I said the input splits, you move the code to the data. So the job tracker says, hey, task tracker, run this mapper and reducer on the data that you have there. So it sort of organizes it so that the code moves to where the data is, does that processing, and then it takes care of tracking the maps and reduces.
Scott, does that mean that the job tracker server is a single point of failure?
No, it means that the name node is the real single point of failure, which is where that secondary name node comes in. It's really more of a snapshot than it's not a failover, it's a snapshot in time. But as of right now, and I think even of 0.21, which just came out, which I thought was supposed to get rid of that problem, the name node is still a single point of failure, which is why you don't want to run all that other stuff on there, because that machine has to basically handle knowing where all the blocks are on all the whole distributed file system and keeping track of everything and getting reports from the data nodes, figuring out when they're down, when new ones are coming on, so on and so forth.
Does the system elect a name node for you, or do you?
No, you have to specify what are called the masters as a master slave. The name node and job tracker, they're the masters, and the data nodes and task trackers are the slaves.
Yeah, so Aaron, do you have like crappy machines for data nodes and redundant machines for name nodes? Like
so they're all the same, but the difference is that the name node servers end up having mirrored OS disks and RAID 5 other disks, and we write those things to both ones, the mirror and the RAID 5, so you can tell Hadoop to write it in multiple locations as well as write it to remote machines. So that way, if you lose the box, you can still after an hour or two of panicking, you can bring it back online. Because if you lose that data, there is nothing in the cluster besides what's in the named-node server that will help you organize all the blocks back together. So all the
you
data
can't go ask all the data nodes, hey, what do you have?
No, they don't know. All they know is they know my block number and here's the block on this. That's it.
All right. So the next couple of slides are just sort of backups to what I just said in case I missed anything. I mentioned single point of failure, bookkeeper. We already sort of saw this, the name node, what it looks like in the UI. The data nodes store the actual blocks. As Aaron just pointed out, they don't know anything about their organizations. Just know I have blocks 1, 2, 3, and 7. Secondary names, it's a snapshot. It's not for failover. As Aaron said, you have to do stuff to bring that back online and essentially swap it in in the event of a name node failure. I think there's active work going on in order to basically alleviate name node being a single point of failure. Brian?
Do you have fragmentation problems on the data nodes as time goes by?
I do not think so, but I don't know for
It's
sure.
like a file system fragmentation, right? As files come and go, do the data nodes know if...
Are you talking about file system and fragmentation in HDFS or on the underlying disks?
I'm talking about an HDFS file. If you go back a couple slides to the data nodes.
No, you can't actually.
Why?
Because
you
allocate,
can't
like,
update
block
the
size.
file.
But can you ever delete?
Yes, you can delete and update and append, but
No, you can't.
you
In
can't
the
append?
end of files, right, would
Alright.
be 64K, right? The
No,
last
they're not
one.
64 meg.
Or
Meg.
64 meg, sorry. 64 meg, right? So you'd have incomplete. Does it do 60? Does it allocate 64 meg every time?
No.
No. Okay.
All right. Job tracker. Okay, we talked about this. One of the things I haven't talked about is speculative execution. So what ends up happening is the job tracker is responsible for tracking all the different tasks across the cluster. So if for a particular job, if it looks and it sees that, oh, I've got these, these mappers running, and I've got 10 mappers, say, and 9 of them are pretty much complete, and there's one that seems to be holding it up. It's taking a long time. What it will actually do is proactively launch that same map task on another node by default and race them. That's the default behavior. If for some reason your mappers have side effects, like for example, one of the things that QL is doing is it's actually directly writing data from Hadoop into HBase data files. Well, you can't have multiple mappers doing it in that case, so you'd have to turn off this feature. But by default, it basically tries to race things against each other if it notices that one is sort of lagging behind, maybe because a disk failed or it's having I/O problems, or maybe the data node's having network problems, or whatever it may be. It will basically try to even out the job if it notices that somebody's lagging behind. Task tracker, that just basically tracks the individual map and reduce tasks. So each different task tracker, you can go and say, okay, I've got individual tasks, map and reduce tasks, and it looks something like this, like task, and then the job ID, which is that sort of timestampy looking thing. A 1-up number is 035, M for mapper or R for reducer, and then another 1-up number on the end for the actual map task number. Okay, monitoring and debugging. So one of the things that's interesting is that when this is distributed processing, so it also means that it's distributed debugging. And so if something fails, you actually have to go to the machine where the particular task failed and go look in its particular log directory. So if you have a particular machine, go to Hadoop home, logs, user logs on that task tracker. So you basically would marry up, attempt, blah, 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 M000. And so I'd have to go to that machine where this succeeded, but if let's say it failed, I'd go there, I'd say cd logs, user logs, to that attempt directory, and inside there, it's got a bunch of files for standard error, standard out, and the syslog. And basically, if you do system out println and system error println, it will put them in there, and then that's just a cat of the syslog. So it's some logging. So it's interesting to kind of do that. You can't just attach a debugger all the time or at all. Another thing that Hadoop...
You want a reduce job that takes all your logs and brings them together?
Sure. Counters. You saw earlier I defined some counters, and one of the ways you can track progress of a job is to define counters, and basically you're just incrementing 1-up numbers, or you're incrementing by some number. So for example, in word count, for every word I see, I could increment a particular counter. So I think I ran this. better word count. So if you remember, so I had two counters. I had a map counter and a reduce counter on the mapper and reducer. So I saw a total of 1.9, almost 2 million words, input words. And the number of unique words in the map phase, and the reason that's there is because the combiners, but the overall number of unique words counted was 58,000. So that's how we, get to basically do different types of counters. And so counters are pretty easy to do, actually. You simply define, one way you can do it is to define an enum, call it whatever you want. So the enum in this case is input words. And the way that you would do this is in the map. So here's where I did the writing out of the key value pair from the mapper. You say context, so use that context object. You say get counter, get the counter you want, and increment it by some number. In this case, we're just incrementing it by 1, but you could increment it by more. Maybe if you were batching stuff up, if you wanted to do that. However you want to do it, though. Okay. A couple of interesting things that I'm not going to really talk too much about, but if you do have tasks, I found out about this the other night. If you have tasks that are failing on particular bits of input data, one of the things you could use is a thing called an isolation runner. And what it would do is save the data around, and it would try to rerun failed tasks with that exact same input data. And you could attach a debugger to that particular thing because you'll try and rerun it on the same node. So that's a case where you could actually do that. However, that means you got to save all the data, which if you have a huge cluster may be kind of not good if you have terabytes and terabytes of data, or gigabytes, or whatever it may be, or petabytes. There's also a way to skip bad records. I really haven't done much with that. But the idea there is that Hadoop tries to be smart about noticing a certain range of records that might be bad, and then say that because maybe you couldn't get everything, you're getting new files in, and so you don't know, and so maybe it tries to say, oh, this range of records is bad. That's going to be, I'm going to skip that. Performance. Talked about speculative execution and combiners. A couple of the things on the bottom. So probably the two on the bottom left are probably the most important. Reducing the amount of input data. So can I actually do a job without all my input data? Maybe I have these files that are like really wide in the number of columns, and I only need to process 2 columns. Well, I could potentially reduce the size of that job by a lot and therefore increase the performance by simply maybe first doing a job to just get those first 2 columns, for example. And data compression. So Hadoop supports compression of input and output files directly, so that way you're not shuffling uncompressed data across the network. You could do compression. And that may or may not, depending on lots of factors, your specific job and the things that you're doing, it may or may not help. So sometimes we're just playing around. We're like, hey, let's turn on compression. And maybe it goes better, or sometimes maybe it doesn't. And also, I'm not going to really talk about that too much, but refactoring code and algorithms. Here's where it actually matters. Maybe different types of algorithms actually can matter a lot when you're processing. If you save a millisecond or 2 or 3 or 10 on a particular mapper, and you multiply that by hundreds of millions or billions of times, it adds up to make a difference, or it can add up. I just wanted to touch on managing Hadoop. I'm not going to go into that too much, but there are lots and lots and lots of configuration settings that you can tune, and you kind of have to. You have to actively manage it. We've actually changed a lot of the, I don't know a lot, but some of the default settings out of the box, which are sort of optimized, at least from what I understand, for the pseudo distributed mode, not a full cluster mode, but everybody in production is going to actually run a full cluster. Scheduling, I'm not running multiple jobs here, but by default it's first in, first out. Which means if you have one job that is basically hogging all the mappers and reducers, then it's holding up everyone else. So there's some different types of scheduling that you can set in there called fair scheduling and capacity scheduling and things like that. And there's some other things as well. So Hive. So for those of us who love relational databases, you don't have to give them up entirely. Hive essentially simulates or provides structure on top of an unstructured data store. So Hadoop, you have these files, and so let's say you have a bunch of comma delimited files. Well, there's some structure to that, and so what you could do with Hive is suck those files in and execute HiveQL, which is very, very, very much like SQL. But it's still not an online transaction processing type thing, because ultimately what's happening is it just translates your queries essentially into a MapReduce execution plan. One or more MapReduce jobs. You can do a bunch of stuff. You can do the same types of things that you can do with SQL. You can do joins, you can do projection, grouping, subqueries, aggregation. One kind of cool thing is that you can do a query and have it input directly into multiple tables as an output. That's kind of interesting. Define your own functions. And this SERD thing, that's for serialize and deserialize. So Matt mentioned the fact that, oh, I might have different files with different types of input. Maybe some are comma delimited, or some are tab delimited, maybe some are images. So you could write your own serialize and deserialize code to basically say, how should I read and split and parse the input records into Hive? So let's take an example. What I have here is a data set from basically patents. And so you have patents that are cited and patents that do the citing. So patent number 3858241 was cited by patent 956203. And so maybe what we want to do is we want to output the number of patents and how many times they're cited and do sort of a histogram of that. So what you could do, let me see, let me go over to Hive. So Hive essentially looks something like, what you'd expect. So it kind of looks like a SQL command line. So if I wanted to do this, forget what the actual shortcuts are. You see they are HC1, 2, and 3. Okay, so the first thing I'm going to do is create a table called demo patent citations. And it kind of looks like creating a SQL table. Oops, let me, that was not good. Okay, sorry. Just want to put it up there. Okay, so create a table that has two strings, citing and cited. And in this case, I need to tell it that the row format is delimited by commas. I want you to store it as a text file. And oh, by the way, the input for this is stored in that HDFS directory. And if you remember how I said that directories, the input to these things are just directories. And so any file under there that's a comma separated file is just going to look at all of those and basically make them all into one table logically. Oops, I think I already did that. Okay, apparently I already did this and forgot to delete them, so the tables already exist there. Describe, what's that called? Demo site. So for example, I can just do a describe on a table. I can see what columns are in there. And I think that this should be OK. So here's an example where I'm actually going to generate a histogram. And so the final output's going to look something like this. So what I'm going to end up with is I'd find something like this. And I could get basically the number of citations that a patent received versus the number of patents. So in this case, the output shows that about 1 million patents received one citation, all the way down to this number is 779. One patent received 779 citations. So this particular query right here, down at the bottom, which is not good, apologize for that. Basically what we're doing is we're saying insert overwrite table demo citation histogram, and then we're doing a select. We're saying, hey, select num citations and the count of them from, and then I'm adding a subselect. So just to show you can do subselects, down here, this right here is going to do a subselect on that initial table of cited and citing. Okay, it's going to count the number, it's going to group by cited and count the number of them, and then it's going to basically say that that citation counts, and then it's going to group by the number of citations and finally order them. And so that's how that output comes about. And so just to show, this basically launches 3 jobs. And you can do an explain on this, and you can see, well, why is it launching 3 different jobs? And they're going to be chained together. It's doing basically one job for the subquery, one job for the outer query, and one job for the insert into the table. And so I'm not going to wait for this to complete because it'll take a couple minutes for it to go through all of those. But this is what we would end up with if we then took that output data and ended up putting it in into numbers. And so if I go over here, patent citation, I think it's that one. So these are the actual numbers. So from running a job earlier, this is the result. So you have one patent was cited 921,000 times, going all the way down to one patent was cited 779 times. Okay. Clouds. All right, so I know that I'm over, but I don't care. That's right, I don't care at this point, because I worked this afternoon to make this work, and it's going to be cool whether you think so or not. So Amazon provides EC2 and S3, and you can either do this all manually, and you can set a whole Hadoop cluster up. You can get Amazon machine images and run, run Hadoop on them. You can use EC2. You use EC2 for the compute nodes for the MapReduce processing, and you can use S3 for storage, or you can move the data up as well. Or you can go, and this is what I did, sort of the Amazon Elastic MapReduce. And this is sort of more of a canned way of doing this kind of stuff. And you essentially launch a job. What I did here is I'm going to launch I launched an interactive Hive job. So if I come over here, so here's EC2. Oh, don't make me do that. So this should go to my Amazon Elastic MapReduce stuff. And so what I've got here are two jobs sitting here. So right here, this Hive job 2, or no, I want Hive job 1, actually has 4 different instances in that cluster. It's using the Amazon small machine image, okay? And so I've got basically a 4-machine cluster up in the clouds. So what can we do with this? So many of you have heard me, and actually some of you have actually gone through this in phone screens or whatever, the billion stars problem. Everybody's like, what the hell is a billion stars problem? And so I'm going to actually show you how we might solve that. So let's actually come over here to this. So the way that you have a command line client, so once you start those jobs in an Elastic MapReduce, if you want to do an interactive session, you can actually use a command line toolkit called Elastic MapReduce and SSH into it. That god-awful number is a job ID, and now I'm SSHing with basically directly into the Hadoop cluster up on the Amazon cloud. Okay, so I've got that right there. It also says that, hey, I can actually access the job tracker and name node via links. Sweet. How awesome is this? So I can actually go in and say, hey, yes, I want you to allow cookies. Come on. And hey, look, we have a text-based system for seeing all this kind of stuff. And same thing, I can also do the same thing for the name node, and I can browse that as well.
What about some SSH tunneling so you can use your own browser?
I don't know. I just did this afternoon, so I'm not sure. But I just thought this was kind of cool, just because I was like, I never really used links that much, so In any case, so once you are SSH into your machine, basically you can start up by saying Hive, because what it's done when I created my job, and the reason I'm not doing it live is because it actually took a couple minutes. Like in one case, it took 10 minutes to spool up that cluster of 4 machines. So I didn't want to sit here and wait for that. But it's basically set up the cluster, a whole Hadoop cluster. It's set up Hive running on the master node. And now I can just do stuff. So I can say show tables. OK. There should be nothing there. Where's my input data? My input data is actually from S3. I have a folder called S3, or called a bucket called billion stars, and it's got the stars data in there. I have a confession, this is not actually a billion stars. I think it's 100 million stars, because that was going to take way too long to generate that file and upload it. And by the way, I found out that generating this stuff, I used Java for it, because Ruby was going to take about, I don't know, an order of magnitude longer with a Ruby script that I had. So that was a case where Java made more sense for that. So
maybe you want to tell people what the problem
yes. Billion stars. I have, Earth is in danger of going away because we're going to be exploded. The sun's going to expand around us and we're all going to die. And so we have a listing of a billion stars. And each line has the name of a star and the distance from Earth, and we want to find the 100 closest ones because we got to get in our starships and go there, our generational starships, because we're not smart enough to figure out warp drive, except on television shows. So BS1. Okay, so the first thing we're going to do up on our cloud is we're going to create a table called temporary stars data, which is going to come from that bucket on S3 billion stars. So I'm going to go ahead and do that. If any of these fail, I'm just going to stop because I won't be able to recover. It's great when you have demos like that. It basically, if any step screws up, you're totally hosed. So okay, so it did that. So if it did, if I could type tables. So we have that there. Okay. Okay. So the next thing I'm going to do is I'm just going to put this into a table that's actually stored as a sequence file. So remember, that was coming in as text, and maybe what I want to do is I want to store it as a natively compressed format sequence file. It's binary, it's compressed, and so I'm going to say create that table, store it as sequence file.
You move this back to the background.
Okay, yeah. So what I just did was that. Okay, so I just created the table. So the next thing I'm going to do is I'm going to say insert overwrite table stars data, select star from temp stars data. So I'm basically just transferring back in there. And oh, that's going to take too long, isn't it? That's going to take too long. Actually, let's go see let's go see here.
There we go, Brian. I like that.
Control R should read.
Show us the code that's running.
Show you the code that's running.
Yeah, the map.
That was it.
That was it. It's Hive, so I'm just doing queries, and it's translate. I don't know what it's doing. It's translating that into the different map and reduce jobs that it needs to do that with, and I don't know why this isn't showing me.
What it's doing is it's running only a map side job, because all it's doing is reading from the text file and writing to a sequence file, which is essentially a character 1 delimited file with nuance.
Actually, I do have a backup, and we're going to switch to it right now. So the thing that I was going to do next, so once we did that, so what we were just doing was this job. We were then going to create this table closest stars, okay, and then we were going to just do this. Insert overwrite table closest stars, select name distance from stars data order by distance ascending, limit 100. And it's going to take care of all that stuff for us. And I actually did run this earlier. I have another cluster, just a 2-machine cluster. Hello. Okay. That one appears dead. Oh, that was interesting. Show tables. Sorry. Show tables. No, I really want... Okay, and so select star. Yes, the delay is kind of noticeable. And so there you go. Because I think that other job is still probably running. You can see it's still going. And what ended up happening earlier is in the reporting here, it usually will go like 0%, 1%, 2%, or so some increment. What happened earlier was it just basically went 0, 0, 0, 100. And we've noticed that can happen if the nodes are too busy to actually report status and things like that from time to time. So that might be why that's happening. But like I said, this job, where is that? That job is going to, I don't know how long it's going to take. So in any case, yeah. So that was the solution to the billion stars problem.
Scott, are you, for the Amazon thing, do you pay?
Oh yes, I'm paying for this. I have no idea how much I'm actually paying for this stuff right now, because I've been running these for several hours. So it.
Gary.
I just wondered if
No, it's actually on my credit card, unfortunately.
Okay, don't worry about it.
Well, you're
CPU time on the machines, or
What's that?
We don't know. He doesn't.
I could figure it out because it'll tell you the normalized instance hours, and there's some chart that tells you the amount of cents you're spending per hour or something like that. I do need to terminate them later, but.
So Scott, I'm assuming the main difference about Hive is the fact that obviously you have to write into a table. There's no such thing as a real query. I mean, the query always writes to a table, I'm assuming.
Yeah, I mean you can do you saw me just do the select right there, right? But yeah, generally you're gonna go into some kind of output table. Yeah, And the thing with Hive is it provides some sort of structure sitting on top of Hadoop. And so obviously it has to be able to understand the file formats that you're dealing with. And what I didn't show in Hive, Hive actually makes joining pretty easy. You can do your left outer joins and your inner joins, and just like you would in normal SQL.
Is it production quality? Do you use it?
Yeah. Well, you know, all these things are like 0.1, right, or 0.5 or 0.6, but you.
Hive was a cute little thing that you just
No,
Facebook uses it.
no, Facebook, yeah, Facebook actually created Hive, and they use Hive to process and analyze their log files. So, yeah, I mean, I think if they're doing it and they created it, it can handle pretty much anything most people can throw at it, I'd say.
Yeah, we're using it to actually build our data.
Yeah. So, Hadoop is HDFS and MapReduce for distributed parallel processing, fault-tolerant, horizontal scale, and Hive can add some structured. There's a whole bunch of subprojects and stuff around Hadoop. Pig is another data processing language. It's not quite. It's more of a imperative language for doing queries as opposed to Hive, which provides a structured way of doing queries. There's a bunch of other stuff in the Hadoop ecosystem as well that I didn't really cover. There's some references, or you can click these links and let Google do them for you. So. Yeah, but that's pretty much it. And I wonder if that job is actually still running. Oh wow, hey, it actually completed. So I could launch another one, but so that's it. Any questions, comments, concerns?
How easy is it to upgrade Hadoop to the next version?
I think it's pretty easy.
Yeah. I don't know how hard it would be if you've got it all over the place. And
Oh,
how would you run multiple instances at the same
what
time?
you do is you end up taking, well, it depends on if you want to do like a rolling start, which is
Harder.
Ambitious, but usually not recommended.
So you just shut it down.
So what you end up doing is you shut it down and you actually put the new version out everywhere beside the old version, and you start up the distributed file system in safe mode where it doesn't make any changes. And then you test things, you make sure you can read files, you do a file system check, you make sure everything's good, and then you cross your fingers, say a little prayer, and then you shut it down again and you bring it up for real. And then at that point, you're committed.
Yeah, because remember, since Hadoop is, it is something that you can bring down, right? Because it's not your online production system right there. So you're doing batching and stuff like that, so you can actually bring it down, as opposed to something like HBase, where that's intended to be more of a real-time thing, which QL is going to do, and I don't know how we'll do updates to that.
Well,
so
the HBase updates are easy because it's designed to do rolling restarts.
Oh, okay.
It's the HDFS file system underneath the covers that makes it update tricky.
And I took Jeff's, this is actually Jeff's idea. He noticed that at the end of presentations, you know, you generally sit, yes, you did this at Ruby Nation. You know, the good thing to do is actually put your name and all that information and the company logo and stuff at the end as opposed to the beginning, because nobody cares at the beginning, and then at the end you have the questions, and so you just leave this up there and it just stays up there forever. So nice little trick from Jeff. Oh, come on, you know you did.
I know, it's an awesome idea.
All right, what'd you get it from, Matt?
No, I don't know. I just forgot that I had that idea.
So, and of course, you know, this works better if it's, you know, at a non-near infinity place, because everybody here is kind of like, yeah.
You kind of glazed over it a little bit there with the S3 integration thing.
I know.
But HDFS is an implementation of the Hadoop API, so you can actually hook it up to any sort of file system that you want. Like if you want to run Luster file system, which a lot of people have done, there's a new file system called FS. It's supposed to be a replacement for HDFS. So you're not tied to any one particular component in Hadoop.
Yeah, so what Aaron said is basically the way that was going through S3 is if you look in the API, they actually implemented a block storage system on top of S3 itself, because S3 file sizes are limited to, I think, 5 gigs per file, which is not going to work for Hadoop. So they implemented, per the Hadoop file system API, an S3 block storage system on top of S3, and that's what the Elastic MapReduce stuff is actually talking to. All right, go eat.